Everyone. Welcome to the National Science Day program, which also culminates our 1 week National Science Day week celebrations at MCNS. Today we have two talks. Both are related to black holes or astrophysics. First one is by Kazuyuki and second one by Professor Ajit Kembhavi at 5 o'clock. So we'll straight away go to the first talk. I would invite Sana to introduce Kazu.
Thank you, sir. Good afternoon, everyone. It's a great pleasure for me to introduce Dr. Kazuyuki Furuuchi, our first speaker today. Dr. Kazuyuki Furuuchi obtained his PhD degree from Osaka University in the year 2000. He was then a postdoctoral researcher at the theory group of the High Energy Accelerator Research Organization in Japan. He then joined as a postdoctoral researcher at the Department of Physics and Astronomy at the University of British Columbia and Pacific Institute for the Mathematical Sciences in Canada. This was followed by a postdoc at Harish Chandra Research Institute in India. He was then a visiting assistant research fellow at the Center for Theoretical Physics, National Taiwan University in Taiwan. Then he joined as an assistant research scholar at the Physics Division of the National Center for Theoretical Sciences in Taiwan. His last postdoc was at the Department of Physics of the National Tsinghua University, NTHU in Taiwan, after which he joined the Manipal Center for Natural Sciences as an associate professor in the year 2013. He has also been a visitor at IHES France and at the Physics Division of the National Center for Natural Sciences in Taiwan. He is also a member of the Particle Physics Group in Japan and the Indian Association of General Relativity and Gravity. He has more than 25 publications in refereed journals, and his research areas include theoretical physics, particle physics, and cosmology. Today, on the occasion of the National Science Day, he will be talking on news from black holes. We welcome you, sir.
Okay. Thank you very much, Sana, for a nice introduction. And I would also like to thank the organizers for giving me an opportunity to present this lecture. And I also would like to thank the participants for attending my lecture. So the title of my talk is News from Black Holes. Yeah, so this lecture, I will focus on theoretical aspects, in particular, black hole thermodynamics and information paradox. And the aim is to bring you to the frontier of research. But there are a lot of things before going to the frontier of research, which we have to learn a lot of things before that. But since the time is limited, I will be somewhat brief on the topics along the way. But sources for other aspects are given in the end. So I start from general relativity, although black hole had been discussed even before general relativity. Well, I cannot make you understand general relativity within this short lecture. I'm just informing you that this is an extremely interesting subject, but you need to probably at least a semester course to understand GR. So if you are a student of physics, you are very lucky, but there are also good textbooks and online materials for self-study. So probably the shortest way to explain general relativity is by John Wheeler. Space-time tells matter how to move, and matter tells space-time how to curve. So matters are somehow trying to move the kind of shortest trajectory in space-time. But since the space-time itself is curved, it cannot go straight. And that is the origin of gravity according to general relativity. And now I'd like to explain black holes in general relativity. So what happens in black hole is, so this is a observer from the distance. And actually the space is kind of moving. So for this person, the space is moving far away, faster than the speed of light. And relativity tells you that nothing can move faster than the speed of light. So if the space itself is moving away faster than the light signal sent from this person would never reach this observer outside. So event horizon is a kind of limit. So beyond this horizon, no signal can reach outside. That is called event horizon. And so since today I will be talking about black hole thermodynamics, let me spend some time on thermodynamics, especially entropy. So what is thermodynamics? Thermodynamics is, in short, physics of heat at macroscopic level. Well, not only heat, we also consider heat and works, but heat is the main thing in the thermodynamics. And there's a first law in thermodynamics, which is nothing but energy conservation. And heat is identified as some form of energy. And probably the most interesting thing in thermodynamics is this entropy, introduced by Claudius in 1865. So this is a change of entropy between two macroscopic equilibrium states, which is given by the change of heat divided by temperature. So yeah, thermodynamics is again a very interesting subject, which you can spend a semester at least to understand. And if you are a physics student, you are lucky. Even if you are not, you have opportunities to learn. So I just inform you that this is a very interesting subject. And so the second law of thermodynamics states that entropy does not decrease, more precisely in thermally isolated system. So this is a kind of essence in thermodynamics, and so you cannot convert all the heat energy to work. There's some limit, and this second law of thermodynamics basically gives you the limit. So the second law of thermodynamics is a law in thermodynamics. Law in physics means it cannot be derived from other laws of nature. But that is within thermodynamics. The second law of thermodynamics may be derived from other theory. And as I mentioned, thermodynamics applies to macroscopic system. In the meantime, people have been long wondering what would happen if we keep on dividing matters into pieces. And the study in this direction led to atomic hypothesis. I have given a public lecture last year in this Science Day occasion. So probably it can be available in the recorded video. So anyway, today I don't go into too much about atomic hypothesis. But note that at the time of Boltzmann, who developed this statistical entropy, the atomic hypothesis had not yet been proven by experiment. And Boltzmann was trying very hard to prove the atomic hypothesis, meaning the things around us are all made of atoms or molecules.
Okay, but I
think 1750 itself that Dalton has proposed the atomic theory, matter.
So it is consistent with that hypothesis, but it's not a direct experimental proof. Rather, it suggests atomic hypothesis or molecular hypothesis.
A particular hypothesis. We have explained the chemical combination laws.
Yeah. Anyway, this I discussed last year. Yeah, so Boltzmann unfortunately couldn't completely convince the other people, but he found this great formula. So this is the entropy, the same as thermodynamic entropy, but macroscopically, it is proportional to the number of microstates, which describes the same macrostate. So macroscopically, like water with some temperature and volume, it is counted as one single macrostate. But for one single macrostate, there can be many microscopic states. Actually, the water molecules are moving and changing the position. So there are many microstates which correspond to the macro state. And so this omega is the number of microstates. And the logarithm of that with some constant coefficient called Boltzmann constant. This is the microscopic explanation of entropy. Okay, now I'd like to come back to the black hole, but let us have fun discussions for a moment. So could you think about any practical use of black hole? Anyone? Practical use, can you think about it? Perfect darkness. Darkness is, what is the practical use of perfect darkness? Eh? Harvesting energy. Well, why? How?
I mean, it has a lot of gravitation. So maybe we can.
Yeah, so like active galactic nuclei in galaxies, supermassive black holes. So yeah, you by converting the gravitational potential energy to heat, it radiates a lot of energy. Yeah. The problem may be how to go there and get the energy. Well, it's not a serious question yet, and yeah, maybe from the story I've told you, a simple thing to think about would be, yeah, basically you can throw away anything you want, then it will never come out. So if you want to make a perfect crime, you can throw evidences into the black hole. Well, practically, it will cost too much to go to black hole and throw away. Another problem is actually close to the black hole, time flows much slower than here. And if you reach the black hole horizon, actually the time freezes. So from outside observer, the things will never go into the black hole. You cannot observe that. So your evidences may stay there, visible. That may not be visible because it will be redshifted enormously. Okay, anyway. Okay, so let us turn to a little bit scientific question. So you might have heard of conservation laws. For example, energy is conserved. You cannot destroy energy. So also, so what about like charges? So you might have heard electric charges are conserved, meaning total number of electric charges. You cannot eliminate electric charge. Whatever you do, the total electric charge is always conserved. But what about throwing electrons, many electrons to black hole, will they disappear? So actually, they will not disappear because electric charges induce electric fields around them, and it reaches infinitely far away. So you cannot hide electric charges into the black hole. The black hole will get the electric charge, and the electric field is induced around the black hole. But that suggests that there are other charges which is not associated with electric fields, or more generally, something called gauge field. So for those charges, there's a chance that the conservation laws, which holds without black hole, may be violated by the existence of black hole. So in the standard model of particle physics, there's something called baryon number. So baryon number may not be conserved. But actually, even within the standard model of particle physics, baryon number is not an exactly conserved quantity. But you can construct some exactly conserved charges not associated with gauge field. And so we don't really know what is the answer, but most physicists believe that those kind of charges, so-called global charges, are not conserved if you consider black holes. Then we come to the central topic of this lecture. So can we throw away entropy? So actually, this kind of discussions happened before, well, Bekenstein found something which I will come to. So yeah, it seems, so Wheeler, I introduced you in the beginning, the one who explained general relativity as matter tells you how the space-time tells you how matter moves. So he has a great contribution to gravitational physics, and also he was a PhD advisor of Bekenstein. So yeah, Wheeler seems to like, well, T very much, and T seems to have played important roles in his scientific discoveries. So here's a hot T and cold T, and if you put them together, the heat will move to the cold T, and the temperature will become the same, and entropy increases. And somehow Wheeler stated that he feels guilty to make both T set to the same temperature because he has committed something which cannot be reversed, meaning you cannot, if the 2 cups of tea become the same temperature, you cannot get it back to hot tea and cold tea without giving entropy to other place. But now we have black hole. So we may throw entropy into the black hole and make it disappear. Then the second law of thermodynamics may be violated. Then we can do a lot of interesting things using black hole. So that was a discussion. But then, yes, actually, you cannot eliminate entropy into black hole. So before this Bekenstein's work, Hawking showed some theorem that the total area of black holes never decreases when you see the black hole merger. And this looks something similar to the second law of thermodynamics, something never decreases. And inspired by this work and also by thought experiments, Bekenstein proposed that black hole has entropy proportional to the area of the event horizon. And Hawking later fixed the proportionality constant, and so the black hole entropy, or Bekenstein-Hawking entropy, is given by the area of the horizon divided by Newton's constant and Hall. And this is in so-called natural units. And it can be rewritten into a suggestive form. So this LP is Planck length, some fundamental length scale in quantum gravity. So area divided by fundamental units of area is the entropy. So this kind of suggests some microscopic origin of this black hole entropy. So, however, in order to really understand this horizon area as entropy, we want to put it into the framework of thermodynamics. Then we also need temperature. But black hole cannot radiate anything. How can it have temperature? Well, black hole cannot, so nothing can come out from black hole classically. But if you consider quantum mechanics, which Professor Suryanarayan taught us last week, so this, due to the quantum effect, actually something can come out from black hole. And Hawking showed that black hole emits black body radiation. Well, yeah, some form of radiation radiated from a body with temperature. So, for example, for Schwarzschild black hole, which only has mass, no electric charge, no rotation, for this black hole, the temperature, Hawking temperature, is given in this formula. And in the SI unit, the temperature for 1 kg black hole is pretty high. But 1 kg black hole is really, really small. For astronomical body like Sun, the temperature is extremely low, so that we cannot measure the Hawking radiation from astronomical body. So black body radiation only has information of temperature. So if whatever you throw into a black hole, you only receive black body radiation. So then the information about something you have thrown out, like your crime, it seems to be lost because we only get back the information of temperature. And Hawking proposed that this is indeed the case. Information is fundamentally lost if you have black hole. This is not that we cannot completely collect all the information physically, but this is a fundamental limit given by the theory. That was his proposal. But actually, if you admit this proposal, information is fundamentally lost. There are a lot of troubles and strange things happen if you consider quantum mechanics. So majority of the physicists believe that information is not lost. However, it had been extremely difficult to show how information recovers or what was wrong in the calculation of Hawking about Hawking radiation. So it has not been settled yet. So earlier I have talked about entropy, thermodynamical entropy, and it can be explained from microscopic level. However, so the question is, black hole seems to have some dynamical entropy. So whether we can get this entropy from counting the number of microstates. So that was a question. And this was partially addressed. Well, there was a success in string theory. So Strominger buffer counted microstates of a macroscopic state that has the same charges to some black hole in string theory, and found the exact match with black hole entropy. So, okay, this work was, so earlier there was a important work of Ashoka Sen for this work. So this is regarded as a great achievement of string theory. String theory is a hypothetical theory that everything in this world is made of tiny string, and different oscillation of strings correspond to different kind of elementary particles. So yeah, so this is a very non-trivial result. You are not really assuming the states of black hole from Bekenstein-Hawking entropy, but sort of derived it from totally different direction, honestly counting the microstates in string theory. Although this black hole is actually a very special kind of black hole, which has a high symmetry, and there's a theoretical control about it. You can calculate many things for this black hole, but this black hole is quite different from the black holes we observe in astrophysics. So there's still a long way to go. And along the way, people found something which seems important in quantum gravity, which is called holographic principle. So in usual system, entropy is proportional to the volume. However, in the case of black hole, the entropy is proportional to the area of the event horizon. So from this observation, Tofuft and Susskind suggested that in quantum gravity, microscopic degrees of freedom live in the not live in the full space, but some lower dimensional space, like a hologram. So hologram is a photo which has information of three-dimensional object, but the information is contained in a two-dimensional photo. So that is the analogy. So quantum gravity in 4 dimensions is described by some theory which has lower dimension. And Madasina in 1997 found a concrete realization of this holographic principle in string theory. So he found that closed string theory in some kind of space-time is equivalent to non-gravitational theory in 4 dimensions. So this example is a concrete example, but well, firstly, the string theory has not been formulated in a complete way. We are somehow studying string theory in a primitive way, we know. And also, solving string theory is an extremely difficult problem. So as far as this conjecture is tested, it never contradicted with this equivalence of 2 theories, but the proof has not been given. So there's a very non-trivial map or dictionary between these 2 descriptions. And this dictionary is still under construction. So there was a latest development for this understanding of thermodynamics of black hole. So Pennington and Armeri, Engelhardt, Maroff, Maxfield in 2019. So showed some way to calculate the entropy in this gravitational theory, which is sort of consistent with the preservation of information. Well, yeah, so this is a big progress towards the support that black hole actually preserves information. But actually, as I said, the dictionary between the gravitational theory and non-gravitational theory in lower dimensions is still under construction. So, and actually this way of calculating is not really directly the counting of microstates, but this is a kind of conjectural way to calculate the number of microscopic states in the dual non-gravitational theory. So this was a big step, but we still have a long way to go, it seems. Okay. In the last part, I'd like to mention some recent observations of black holes. So not the theory, but observation. So yeah, so the LIGO detected gravitational waves first in 2015 from black hole mergers, and also subsequent events of black hole neutron star mergers. So now there are a lot of observational data about that. So this is how it looks like, the gravitational wave. And they were awarded the Nobel Prize in Physics in 2017. And also the Event Horizon Telescope observes the shadow of the black hole. So not directly the black hole, but the bending of light around the black hole. So this topic is will be discussed in the next lecture today by Professor Ken Barbie. So stay tuned. So although observational data of black holes are not as plenty as theorists wish, but efforts have been made to constrain gravitational theories from those data. Okay, so this is basically what I wanted to talk today. So for other aspects of black holes, so 5 p.m. today, right after this talk, there will be a lecture by Professor Ajit Kembabi, the bending of light and the first black hole image. And also, Dr. Devi Joy Bhattacharya at our center, MCNS, has given a talk on black holes before general relativity, Chandrasekhar limit, supermassive black holes at the center of our galaxies, and many more. So yeah, there might be a recorded video, or if not, you can ask him to give a lecture again. And we now also have Dr. Chandrachur Chakrabarty, and he's an expert in general relativity. And I think he likes singularities in general relativity and many more, such as sound analog of black hole. So yeah, you can also ask or attend the lectures by them. And I'd like to dedicate this lecture to the memory of Professor KPN Murthy, who was associated with us earlier, and he passed away last July. So Professor KPN Murthy was a respected researcher and a great teacher. We had nice discussions on thermodynamics and statistical physics at MCNS here. And at that time, he was also interested in black hole thermodynamics, and we talked about discussing about it some later time. But yeah, we didn't have discussions about that. So probably this lecture was too late, but I dedicate this lecture to Professor J.P.N. Murthy. Okay, so this is what I wanted to talk today, and these are references for further study. So Professor Murthy wrote a nice book, Excursion in Thermodynamics and Statistical Mechanics, University Press. And also the homepage of Professor Murthy at the Chennai Mathematical Institute is still available, and he has a lot of lecture notes and talk files. So yeah, if you got interested, you can look there. And this is a popular book, very nice popular book about black hole and gravitation. And this is kind of quite along with today's lecture for the earlier part of the theoretical development. And these are latest developments, what is really happening now. Okay, yeah, thank you.
Thank you, Kazu. You can take a few questions, right?
Yes.
Yeah. So firstly, those who can't remember all these references, remember all this is there on YouTube, going live. All our videos are saved in our channel. You can search for Dr. TMAPI Planetarium, and you can note down all this. Don't worry about if you forget all these links and references here. It's all saved in YouTube. Okay.
I have one comment and one question. The comment is, recently using the anti-de Sitter space, they have shown, people have shown using conformal theory. It can be, you can derive the properties of quark-gluon plasma, eta by S, and viscosity of the quark-gluon plasma. That's a very important recent discovery, 2012-13. My question is, are black holes formed after the Big Bang or during the stages of cosmology, cosmological evolution? The universe is as it expanded. And new black holes are formed, or is it? Are any new black holes are formed, or they are formed micro black holes at the time of Big Bang and then they are expanded?
Yeah, so black holes can be created in different sizes, and so we have observational evidences for astronomical size black holes from like solar mass black holes to supermassive black holes. These are created after much later. For the supermassive black holes, actually, how they evolved are still remain as quite a mystery. They seem to have grown much faster than we can currently theoretically explain, and there are a lot of proposals about it. For much smaller size black holes, so people discuss as primordial black holes. So these might have played important roles in cosmology, such as dark matters, but so far there has not been observational evidences. And okay, so that's about black holes. And about the first comment, yes, indeed, that is what I discussed, ADS. But so, yeah, so string theory, people try to claim that they have predicted this property of quark-gluon plasma before experiments at Rick and others. Yeah, that's sort of good, but yeah, this ADS, so-called ADS CFT correspondence has not been completely. Well, assuming it and used it and it got success, but yeah, it's like a phenomenological model.
But it is very successful, very successful.
It is successful, but it's a phenomenological model, successful as a phenomenological model. But actually, a little bit like number of parameter space, you are looking at the limited number of parameter space, but actually that may not be justified. And also the approximation, they are, I think, only calculating the zeroth order approximation, meaning you don't know the order, the size of the collections. That's what my impression. I'm not very sure, but yeah.
I have another question. I want you to comment on that. At CERN, LHC lead-lead collisions, some people have calculated a micro black hole can be produced. So that's why I asked in the time of Big Bang, micro black holes are produced or not. So they were trying to look for evidence in the lead-lead collision whether any black hole will be produced and it will expand and eat away the entire universe.
Right. So yeah, many people have worked on the theory beyond the standard model of particle physics, and one direction is that the quantum gravitational scale is actually much smaller than the so-called quantum Planck scale. That happens when the extra dimension size is pretty big, bigger than usual scenario. And in that case, many small elementary particle scale black holes will be produced. And yeah, so that was seriously investigated, and so far LHC did not find. And also, many people worried that if black holes were produced in LHC, whether these black holes will swallow the Earth and whether it is dangerous. And there was also a kind of safety study about that. And well, we already have some ultra high energy cosmic rays, whose energy is much, much higher than the energy produced at LHC. So and there has been no problem about that. So of course you can consider very exotic scenarios about black hole creation, but well, it should be extremely, well, essentially no harm. And usually small black holes will be just immediately radiate away by this black Hawking radiation and disappear.
Dr. Kazu, this is not a question. Out of curiosity, I'm asking, who coined the word of black hole?
Okay, so actually, the name black hole, who coined that, often it is attributed to this Wheeler appeared. This Wheeler, who has made a big contribution to gravitational physics. But it seems it has actually been appeared earlier in some writings, but yeah.
Yeah, I think I remember that Subramanian S. Chandrasekhar, that limit is there, who just coined this word of black hole, knowing incidences in India at Calcutta. I mean, I just read something, kind of article. It's not scientific.
I do not know. What?
Yes, Chandrasekhar. You know, yes,
yeah, Chandrasekhar I know, but the name was.
No, but actually, the black hole name is coined by Wheeler, not Chandrasekhar. Okay. So it is related to, yeah, I remember it is related to some incident related to Kolkata, yeah. But this name the black hole coined by Wheeler, not Chandrasekhar.
Yeah, well, majority take that, but yeah, actually it appeared in something much earlier, and like Dicke seems to have mentioning something like that black hole. We got mentioning Calcutta actually, but I'm not very sure, like good at historical anecdote. So. Yeah. The backward name is appeared. Okay. Point by Wheeler.
Yeah, Wheeler, not
separately, right? Not.
Yes.
Wheeler mentioned in some lecture.
Yeah, there is a paper appeared in the archive. I think 3 or 4 years ago. Mm-hmm. So it is mentioned that this black hole, this black hole phase is related to an incident of Kolkata, but that name actually given that black hole is by who?
Okay. Thank you.
I have one more question. So a lot of things go into the black hole. It is swallowing everything, all physics information, everything. But it will come out, completely come out. It will completely evaporate whatever information it has taken. Full entropy will come out. Or
so that's what
so
most physicists believe. Well, no one has succeeded in showing that. But if information is lost, that means it is not an unitary evolution. So, well, then it cannot be put in a quantum mechanical framework. You have to invent something beyond quantum mechanics, but many people think it's unlikely. Also, energy conservation will be in danger, and also time reversal symmetry may be broken, and a lot of weird things happen. So many physicists don't like. And in fact, Hawking and Thorne and Presque made a bet whether information is lost or not. And Hawking admitted that he lost, although Thorne was not convinced by the Hawking's argument, and he, I think, maybe still admitting that he lost. So Thorne and Hawking were on the sides that black information will be lost.
Couple of years ago, we had an image of black hole displayed in all the newspapers.
Yeah, very recently.
Yeah. How was that generated? What was the kind of obviously it's not a photograph, but then it has been generated through certain other electromagnetic radiation spectrum.
It was observed by radio telescope. So yeah, it's a topic of Professor Kenbabi, so maybe we can wait for his lecture. Yeah, David Joy also gave a talk about that. Yeah.
I mean, some of the light which is bending very near to the black hole are coming back, and actually the black portion is the region from where the light cannot come back. So that is called actually black hole shadow. This ETH is one event horizon telescope. So this is a combination of 3 telescopes probably, and the longest baseline, which is diameter is as equivalent to the radius of the Earth, or I mean the dimension of the Earth. So it was done through this way, and of course it was matched with the theoretical prediction about the how should it look like.
Yeah, so it is same like GMRT which India have, but the baseline of 2 antenna is almost the diameter of the dimension of the Earth. Now that is VLBI technique, which is called yes. So very long baseline technique. So that is the same thing which is GMRT is operating, but it is in high frequency.
So the next lecture is exactly about this, the first imaging of black hole by Professor Kenbabi. So I hope he will explain in detail. Any more questions? People on Teams can unmute themselves and ask questions if there are any questions. Feel free to unmute yourself and raise your questions. Okay. Meanwhile, they think about question. I'll ask one question for the gallery. There are a lot of scientists, who think that this whole singularity theory itself is all wrong and nonsense. They think that all this thing can be explained with a very massive object with heavy gravitational field. All these things can be explained with such an object. It need not require any singularity such things theoretically. So what is so that there is no black hole as such? It is very heavy gravitational object there. What do you comment about that?
I don't know about much about these alternative explanations, but firstly, general relativity has been tested in many many observational and experimental data. So general relativity is correct under some known regime, and assuming general relativity is correct, there's a singularity theorem, and well, there's a condition that singularity develop. So, well, I think you have to modify the theory, I think, and but that theory, well, general relativity is already tested in many ways. Well, many ways, but I don't know whether those alternative theories have been tested. Any more comments?
Actually, there are many papers published by Ricardo. It is possible to explain something considering those type of objects that are not the black holes, but but they actually did not mention that black holes are not observed. I mean there are some other objects which can mimic as black holes, but there may be some objects which can mimic black hole, but they actually did not rule out this existence of black hole.
Yeah, I would say that current general relativity is more trustable than those alternative theories.
I have heard few talks by Abbas Mitra going around saying this is all wrong.
Abbas Mitra was one of our colleagues. He was telling singularity-free general relativity.
The
theory he proposed. It came in Foundations of Physics, one important paper he published. I have one question. This is my last question. I will not ask anymore.
Well, fine.
There is one more lecture. Wait.
My question is, I asked you already about whether information is lost in the black hole, because people, physics believes that the entire universe is an isolated system, for which according to laws of thermodynamics, entropy should increase. If black holes exist, total entropy is, forget about increasing, not even constant, it will decrease. Then what is physics then? Is physics, thermodynamics valid for the universe as an isolated system?
Well, actually, firstly, the current form of thermodynamics is not applicable to the whole universe, because the thermodynamics talks about the change of state between equilibrium states. So in the middle, it can be non-equilibrium, but the first initial state and final state should be equilibrium, and that is not achieved in the universe. So actually, it's wrong to apply thermodynamics to the current standard thermodynamics to the whole universe.
Okay. So no questions from people on Teams, right? Okay. If there are no questions, we'll break for tea and assemble back at 4:55 for the final session of our week-long celebrations of National Science Day. At 5 p.m. for Professor Kampavi will be continuing basically where Kazu stopped. Yeah, it's a different aspect of that, which is observational aspect of black holes more of. Thank you.